Hey, welcome back everyone. So in this video, we're going to focus on the last learning outcome of the chapter, which covers other continuous probability distributions. We will focus primarily on the exponential probability distribution. So let's get started. In this section, there are two other continuous probability distributions that are discussed in the textbook. These are the uniform probability distribution and the exponential probability distribution. We won't be learning how to do the uniform probability distribution, but it's useful to know what it is and where you might see it. So the uniform probability distribution is used when we don't have very much information, and so we can assume that the probability of any interval or range of continuous random variables is the same for any other interval or range of the same width. So in other words, we assume all of the variables have the same chance of occurring. So the exponential probability distribution, which we will focus on, is used to measure the time that elapses between two occurrences of any event. So let's review some examples. So one example might be we want to know the time between hits on a web page, or the time between arrivals of customers at a bank drive-in teller window, or the time between failures of an electric component. So all of these can impact business decision making. For example, is our web page getting enough hits? Do we have enough tellers for all of our arrivals of customers to a window? And then lastly, is the time in between failures a long time or a short time? And does something need to be fixed in a particular component? So here is the exponential density function. So we have our formula that is f of x equals lambda times e, which is our natural log, to the power of minus lambda times x. So lambda is a Greek letter here that we have not seen before. The exponential density function assumes that x is greater than or equal to 0 because you really can't have a negative time, right? So fortunately, we don't have to worry about this formula too much, but I just want to introduce it to you so you have at least some familiarity with it. Another key concept here is that 1 over lambda is the mean time between events. Note that the standard deviation of any exponential distribution is the same as its mean. So for our exponential probability, this is the probability that a value will fall within an interval is the area under the graph between 2 points of that interval. So this formula is useful because we can find the exponential probability with a simple calculator. And so this is the probability that our x is between 0 and some value of interest. So let's suppose between 0 and 15 minutes or 0 and 2 hours. The formula then is 1 minus e, our natural log, raised to the power of negative lambda times our a, or our value of interest. So what does the exponential distribution look like? So as this picture shows, it kind of looks like a ramp with different levels. As we saw earlier, the mean is just 1 over lambda. So as lambda gets smaller and the mean increases, the ramp gets flatter and the shape of our exponential distribution. So like all distributions that we've been working with in Excel so far, it always gives the cumulative probability from left to right. This is something that's pretty consistent within Excel. So let's look at an example problem 6.37 in the textbook. The time between phone calls to a cable television call center follows an exponential distribution with a mean of 1.5 minutes. So in part A, it asks what is the probability that the time between the next two calls will be 45 seconds or less. So first, we must figure out what is our lambda. Lambda is equal to 1 divided by the mean, and so we're going to take 1 divided by 1.5 minutes, and we get a lambda of 0.6667. So in this problem, it described the time in minutes for the mean, but then in our question, it talks about time in terms of seconds. So we need to make sure to convert our time so that we're working consistently within the same units of measure. So 45 seconds or less is the same thing as saying 0.75 minutes, and I get that by taking 45 seconds divided by 60 because there's 60 seconds in a minute. So this is our A in the formula, or the event of interest. We will now plug in our values in the formula to find the probability of x being less than 0.75 or 45 seconds. We'll first do the calculations in the exponent, so we'll take negative 0.6667 times 0.75, and we get a negative 0.5. So next, we're going to take e, or 2.71828, to the power of negative 0.5, and we get 0.6065. Then finally, 1 minus 0.6065 equals 0.3935. Now, let's do the same problem in Excel. So you can either type directly in the formula bar or use the formula builder. We need to enter our x of 0.75, our lambda of 0.6667, and then true for cumulative. And as you can see, Excel returns the same answer as before, or 0.3935. Let's go ahead and do part B for the same scenario. We have a call center with an exponential distribution with a mean of 1.5 minutes. Note though, in part B, we're asking what's the probability that the time between the next two calls will be greater than 112.5 seconds. So we have simplified the formula here from before, and now it's just going to be e to the power of negative lambda times a. Lambda will be the same as part A, where we take 1 divided by 1.5 minutes, and we get 0.667. Like before, the problem is looking for seconds, but our mean was given in minutes. We know that there are 60 seconds in a minute, so we take 112.5 seconds and divide by 60, and we get 1.875 minutes for our A, or our event of interest. We will now plug in our values in the formula to find the probability of x being greater than or equal to 1.875, or 112.5 seconds. We will first do the calculations in the exponent. So we take negative 0.6667 times 1.875, and we get a negative 1.25. Then we'll take e, or 2.71828, to the power of negative 1.25, and we get 0.2865. So let's wrap up this problem and do part B again, this time in Excel. So down here at the bottom, we have our exponential distribution, and it's notated that 1.875 on the line with a blue arrow. So if you recall from the prior slide, 112.5 seconds converted to minutes is 1.875 minutes, which is our event of interest. So we can write our probability statement as P of X is greater than or equal to 1.875. So here's our Excel inputs again, and as a reminder, you can either type them into the formula using the exponent.dis function or using the formula builder in Excel. We will put 1.875 for X, 0.6667 for lambda, which we calculated before as 1 divided by 1.5 minutes, and then true for cumulative. And as you can see, this returns 0.7135. So are we done yet? Well, if you recall, Excel always gives us the cumulative probability from left to right. So that is this area to the left of the 1.875 notated by the blue caption. Now, we've done this many times before, but we can use the complement rule again and take 1 minus 0.7135, and we get 0.2865, and that matches our answer from the prior slide. Now, that represents the area to the right of 1.875, notated by this green caption. So that can be a little tricky to understand because when we did it manually with the formula, we removed the 1 minus to simplify it. So that will make more sense with some practice. So let's wrap this up and discuss a summary of the different probability distributions that we've learned in Chapter 5 and 6. So in Chapter 5, we had the binomial distribution and the Poisson distribution. We did not do any practice problems with the hypergeometric distribution, but we learned when we might need to use it. These are all random variables based on counting. Then in this Chapter 6, we learned about the normal distribution and the exponential distribution and how to use them. We only touched on the existence of the uniform distribution. These are used when our random variables are uncountable and determined by measuring. Well, that wraps up this video on the exponential distribution, and that also wraps up Chapter 6.